and turn these in for extra credit, and I encourage you to do that. So we're going to do this computer vision one, and we're going to use this clothing database, Fashion MNIST. This is these little 28 by 28 grayscale pictures of clothing. There's a bunch of them, and they are sorted and labeled in categories like t-shirt and trouser and dress and sandal. So you have, this is called supervised learning. You have examples with labels, and you're trying to train the machine to sort these into those categories. So here's what it looks like. You have the input image. It's 28 by 28, so that's 784 pixels. Those 784 pixels are brought out into separate elements of input. Those are the inputs. Then you have a layer of hidden neurons calculating them, and then you're going to have 10 outputs, and the output of these will be the probability that it is a coat or a sneaker or a bag or the other choices. So we're going to train that, and as you see, it is very much the same using the Keras model. So here I define the training images and training labels, test images and test labels by loading the data, which is included in the library because this is a standard machine learning task to practice on. And then the original images have integer values of each pixel going from 0 to 255. But in machine learning, you usually like to normalize everything so it goes from 0 to 1. So we divide it by 255 to make these have the standard expected size of variation. And then we make a sequential model where first it's going to flatten the 28 by 28 down to 1 by 784 because the model likes to have just one line of neurons coming in. This is the input. Then I'm going to have one hidden layer with 128 neurons to do the calculation, and then 10 output neurons to indicate the probability that it's in any of those categories. And the softmax activation function will normalize it so that the output probabilities all add up to 1. Then we're going to compile the model. We're going to measure it with cross entropy, which is how you measure success on a multiple category classification task. You calculate the negative log of the probabilities that you're getting each one of those 10 things right, and that's a measure of accuracy. It's a number which you can maximize when you have the highest quality fit. And we're going to use an optimizer called ADAM, which is a more complicated, the stochastic gradient descent just took little steps of a fixed size. The ADAM changes the step size as needed, so it converges in fewer steps, but each step takes more calculation. Then it's going to fit the model, and then it's going to evaluate it. When you have training data with labels, you split it into two sets. You take usually about 70% of the data and use it to train the model, and then you reserve 30% to use as test images, which you don't show the model until after you're done training. Use them to see if it's actually learned well or not. So that's what this will do. And you can see when these things run, it's getting ready, and it's going to put a little, there, it shows what step it's on. Here it's importing a library. You see the little green triangle indicating which Python command is happening. Then it's doing the training image. Now it's fitting the data. Okay. And here it is doing the first of 5 training epochs, and each one takes about 10 or 12 seconds to do here because it's doing a lot more calculation with this model. And you see the loss. The loss here is this entropy measure, and so the loss is 0.5, but it's going down. As the loss goes down, the accuracy goes up. This is the percent of the training data that was correctly categorized, so it's 82%, 86%, 87%. The training data is getting more and more fit until we get 89% accuracy on the training data. And then when we try the test data, it's 87%, so that's pretty good. That means it has learned something, and it generalized pretty well. If the training percentage is much higher than the test percentage, then you have overfitting, and that's what we're going to do next. This is where this all is less mathematical and scientific and starts having some human results. But first, let's see which ones it got wrong. This is going to show the results for the first 20 images, so we can understand what the model did. So what this is going to show you is this is the output. This, so what you're seeing is the probability that this image is in category 0, 1, 2, 3, 4, and the first number is the right answer. So this image should be in category 9, and as you can see, category 9 is the biggest number, but it's only 54, so it almost confused this with category 7, 40%. So it got it right, but not by much. These ones it was very sure about. I'm trying to find one it got wrong. This one looks like it got right. This one it got wrong. See, it has a 70 here in column 2 and a 27 in column 4. So it was really a category 4, but it misidentified it as a category 2. So this is 0 to 19. This is image number 17. So I'd like to look at the first image, which it got right, and image number 17, which it got wrong, so maybe I can understand why that's happening. So here's the code that will show you that. And it's image number 17 that I got wrong this time. You might get different ones wrong each time. There is some randomness in the calculation. So, all right, so this is the one it got right, and that's the one it got wrong. And you can see this looks like a shoe. You might be confusing it with a sandal or something. In fact, this is the one where it should have been category 9, but it thought perhaps it was category 7, so let's see what those categories are. Category 9 is a boot, and category 7 is a sneaker, so that makes sense that it can't really be very sure that that's a boot instead of a sneaker. And this one was really supposed to be category 4, but it misunderstood it as category 2. And category 4 is a coat and category 2 is a pullover, and I don't even know if I understand the difference between those two either. So again, it's understandable how the machine learning model will have difficulty categorizing two things that are so similar in shape. So that shows the flaw there, and now I'd like to show you overtraining. So this, you might think that the more you train it, the better it will get, but it's not that simple at all. If I just train it for 25 epochs instead of 5, let's do that. So I take this model here, which was trained on 5 epochs, and I train it on 25 epochs. So I'm going to do a whole lot more work training it. And this will take a few minutes to run, but I think I'll just jump to the result. The result shows you a flaw here. It will actually get much better. Remember, up here, the accuracy of this one with 5 epochs of training was 89% on the training data and 87% on the test data. So that is a good model where you have got to a pretty good accuracy, and your ability to predict new images you've never seen before is about the same. But if you do more training, then you will get to like 94% on the training data, but only 88% on the test data. So what you have done with overtraining is you have fit the little details in these particular training images that really do not represent the class. So if you more training, the more accurately you get on the test data, but you'll be learning bad habits that do not really generalize. This is what's called failure of generalization. When your model can handle the training data, but when presented with new data to classify, it doesn't behave very well because it has learned to focus on the wrong little details, not the general trend. So that's overtraining. And there's some flags to find here. So you can also see, by the way, how many parameters there are. This image training model has 101,000 parameters. So it's really got a lot of calculation to be done, and it's amazing how fast this is these days. So that's what I wanted to show you about these extra credit projects you can do. And I'm not going to do any more lecturing today. I'll just answer questions as they come up.